Okay, so we're jumping into homework help again, or classwork help. So we did the I do and the we do together in class. So I'm going to start with number 1 of the you do activities for homework. So we have this reaction between these imaginary things, our CHAP decomposing into CH and AP. And it tells us that it occurs in a single elementary step. Since we know that it happens in an elementary step, we know that we can use the stoichiometry of the reaction in order to write our rate law. So we're going to write that rate equals K times the concentration of this CHAP. And because our coefficient is 2, we're going to raise that to the second power. So this is a second order reaction with respect to CHAP. So moving on to the next part, we are going to write a rate law for this reaction for the decomposition of ozone with nitrogen monoxide, given that it's an elementary reaction. So again, it's an elementary reaction. We know we can use the stoichiometry of the balanced chemical equation. So we're going to write that the rate is equal to our constant K times the concentration of ozone raised to the first power times the concentration of nitrogen monoxide also raised to the first power, and we're done. Now, this one goes into mechanisms, which we haven't really talked about yet, but we did talk about adding up steps in order to find the overall reaction. So if we look at these two proposals, we can see that in this one we have 2A reacting to form C, and we have C and D forming to react A and B. Now we see that we have C on both sides, so when we put it together, we're going to get 2A plus D yields A plus B. Now let's confirm that we get the same thing with this proposal. So here we see that we have 2A reacting with E to form diatomic A, so and we have that same diatomic A reacting with D to form A and B and E. And we see that we have the diatomic A on both sides, and we see that we have E on both sides. And this gives us that same reaction, 2A plus D yields A plus B. So an intermediate is something that is produced in one reaction and consumed in the next. So we see that C is produced here and consumed here. So in proposal 1, the intermediate is C. In proposal 2, we can see that when 2 A's react with E, we get diatomic A, and so diatomic A is our intermediate. Predicted rate law for this elementary step, we're going to use that the rate is proportional to the stoichiometry because it's an elementary step. So we would say the rate is equal to K times A squared. Elementary step 2, we would say that the rate is equal to C times D. Oops, I forgot the K. And we don't want to forget that. So all we're doing is using the stoichiometry of the equation. Later on, we'll talk about how we eliminate intermediates from from rate determining steps, but for right now, we're just writing the reactions as we see them. Predicted rate law for elementary step 1 here would be that the rate is equal to K. Now, because we have a coefficient of 2 here, we're going to have A raised to the second power times E, because this is elementary step 1. And then we have a predicted rate law for proposal 2, elementary step 2. So here our rate would be K times the concentration of diatomic A times the concentration of D. So it says if the observed rate law for this reaction was found to be rate is equal to K times A squared, which proposal is correct and which step is the slow step. So again, we haven't quite gotten here yet, but we'll just go over this quickly. So if we have a mechanism, the way we confirm that our theory, our proposal is right, is that the rate law of the overall reaction will match the rate of the slow step in the correct proposal. So, which proposal is correct? Well, we're looking for one of these steps to match this rate law, and we see that that's this one right here. So that tells us that proposal 1 is correct, and that this step, the 2A forming C, is our slow step. So we would say proposal 1 is correct, and the slow step is step 1 because that's the rate determining step. That's the slowest step. That's the one with the highest activation energy. Okay, so when we talk about reaction mechanisms, we have two proposals here. One is that it happens all in one step, the reaction of iodine monochloride with hydrogen gas to form hydrogen chloride and iodine, or that it happens in 2 steps. Iodine monochloride reacting with hydrogen to form hydrogen iodide and hydrogen chloride, and then the hydrogen iodide reacting with iodine monochloride to form hydrogen chloride and iodine. And it says, why is choice B a more likely mechanism? Well, what's more likely? 3 molecules crashing into each other with the correct orientation and sufficient energy, or 1 molecule crashing into another molecule with the correct orientation and correct energy? Just from probabilities, this is much more likely because it is a bimolecular reaction instead of a termolecular reaction. So, bimolecular reactions are much more likely. And so if we assume that B is correct, we would write our predicted rate law based on the slow step from this one. So we would write that rate is equal to K times iodine monochloride times hydrogen concentration. And so that would be our final answer. Again, because this one is more likely because it's more likely to have 2 molecules with the correct orientation and energy crash into each other than 3. Okay. And that finishes up our elementary reaction questions, and we're moving on to our questions about collision theory. Is that right? Yes, it is. We're moving on to our questions about collision theory. Okay. So again, we did the we do together, so we are going to move on to the you do. So it tells us that the conversion of chloroethane to bromoethane is bimolecular, and it asks us which of these sets of reaction conditions would result in the highest reaction rate. So, remembering that collision theory tells us that we want to have the most collisions with the correct orientation and the correct energy. So, if we look at first at number of collisions, so number of molecules and concentration is going to affect the number of collisions. So, here we have 2 moles in 2 liters. Here we have 4 moles in 4 liters. And here we have 2 moles in 4 liters. So this is the least concentrated, and it's at a lower temperature. So that is not going to increase the number of collisions. Here we have the same concentrations because we have 2 moles in 2 liters and 4 moles in 4 liters. But this one is happening at a higher temperature. And so experiment 1 and experiment 2 have the same number of collisions, but experiment 3 has more experiment 2 has more energetic collisions. So I would say number 2 because it will have the most collisions, and those collisions will have the most energy. And that means that more of our collisions are likely to be effective, meaning they'll have enough energy to surpass activation energy. Okay, now we have our scientists calculating that 10% of the collisions that occur for a specific reaction are in the correct orientation, but experimentally the number of reactions that occurred was much lower than their calculation. So what did they not account for? Well, we have to remember there are two things required for an effective collision, and those two things are correct orientation and sufficient energy. So we talked about the correct orientation, but they forgot to account for sufficient energy to overcome activation energy. So remember, always two factors when we think about an effective collision, and that's sufficient energy and correct orientation. All right, number 3. It says that in this reaction, the dimerization of nitrogen dioxide, the rate of reaction was slow with 2 moles of nitrogen dioxide in a 2-liter container at 1 atmosphere and 285 Kelvin. So it asks for 3 different ways to increase the rate for the reaction and explain by referencing collision theory how each is going to alter the rate of reaction. So way number 1, increase the temperature. And with respect to collision theory, why is that going to alter the rate of reaction? Well, increasing the temperature is going to mean more collisions will have enough energy to overcome activation energy. And then another way to increase the rate would be to increase the concentration or the number of moles. And the reason that that's going to increase the rate of reaction is because if we have more molecules, we'll have more collisions. And if we have more collisions, there's a greater likelihood that some of them will have sufficient energy and correct orientation. We could also add a catalyst. Adding a catalyst can work in a couple of different ways. It can work by improving orientation, or it can work by decreasing activation energy, both of which will result in more effective collisions. We could also increase pressure or decrease volume. By decreasing the volume, we would increase the number of collisions because we're going to put our particles closer together, and increasing the number of collisions will increase the number of effective collisions. Anything we can do that increases the total number of collisions is also going to increase the number of effective collisions. Okay, so that was 4 instead of 3, just as you guys have answers. Alright, so now, last question says that methane doesn't react with oxygen in the air until a striker or a flame is brought near the Bunsen burner. And you guys have had experience with this in the lab. So what's the role of the striker or the flame? It's to provide activation energy. And what is the role of activation energy? Well, in order for methane to react with oxygen, both the C to H bonds and in methane and the oxygen to oxygen bonds in oxygen have to be broken before new bonds can be formed. And it requires energy to break those bonds. So the activation energy breaks those bonds so that forming the new bonds can release energy. As always, if you have any questions, let me know.